Welcome developers, data architects, and computer science students. Whether you're battling a stalled production cluster at 2 a.m. or facing a brutal technical interview, you're in the right place. In this explainer, we're breaking down the definitive diagnostic playbook for systematically fixing slow Spark jobs. Let's jump straight into it. Before we get into the weeds with specific rules, we really need to understand the big picture. We'll be exploring the entire optimization landscape today. We're moving from choosing the right data structures all the way to coalescing partitions and leveraging adaptive execution. Literally everything we cover is going to map perfectly back to this core ecosystem.
To get there, we're structuring this explainer like a true diagnostic manual. We'll start with the foundational mindset, move quickly through the 4 critical optimization patterns, that's shuffle, joins, data skew, and memory, and then wrap the whole thing up with a bulletproof pre-flight checklist.
Okay, let's kick things off with Section 1, the optimization mindset. We need to lay some ground rules.
Listen, Spark optimization, it's not about randomly tweaking configs and just crossing your fingers. It is a highly systematic process. When you're staring at a stalled cluster or sweating at an interview whiteboard, the secret is to step through these 4 questions in this exact order. Ask yourself, is there an unnecessary shuffle? Is the join strategy correct? Is there data skew? And finally, is memory being used wisely?
Think of this matrix as your ultimate cheat sheet. It perfectly maps real-world symptoms directly to their root causes and the specific fixes you need. If a job drags after a join, you're almost certainly dealing with a heavy shuffle, so a broadcast join might be your ticket. If one task hangs forever, yep, you've got data skew. Keep this exact correlation in mind as we break down these individual patterns.
That brings us nicely to our first major pattern, shuffle optimization. The ultimate goal here, reduce data movement.
Shuffle is basically always the prime suspect when you see insanely long stages, sudden disk spills, or massive network wait times in the Spark UI. It's triggered by wide operations, things like group by, join, distinct, or order by. Basically, these commands force massive chunks of data to physically travel across your network to different machines. It is incredibly slow. To fix it, you absolutely must reduce your data size proactively and accurately tune your shuffle partitions config to match what your cluster can actually handle.
Now, here's a classic interview trap, the difference between repartition and coalesce. While repartitioning forces a full, incredibly expensive data shuffle across your entire network just to rebalance data, coalescing is totally different. It safely reduces partitions locally on the exact same node. It essentially combines the data without moving a single byte across the network.
So if you take absolutely nothing else away from this first pattern, let it be this golden rule. Always prefer coalesce over repartition when you're trying to reduce partitions after wide aggregations. It will save you a tremendous amount of processing time.
All right, let's pivot to pattern 2, join optimization.
Joins will absolutely dominate your job runtimes, and choosing the wrong strategy will flat out crash your application. So let's talk about the broadcast join pattern. Imagine just sending a tiny copy of a reference table to every single worker node. By doing that, the join happens locally, right where the data already lives. You completely bypass that slow, agonizing shuffle phase across the cluster. It's brilliant.
But wait, there's a huge trap here. You can only broadcast truly small tables. If you try to broadcast a massive table, you're going to instantly overwhelm your limited executor memory and boom, severe out-of-memory errors. Your job will just immediately fail.
Moving right along to pattern 3, data skew. This is where we tackle those pesky dominant keys.
Data skew is literally the worst. It's this frustrating situation where just a handful of keys totally dominate your dataset. This means one single task runs much longer than the rest, holding up the entire stage while the other nodes just sit there. You can easily spot this in the task view of the Spark UI. Once you find it, you can fix it manually by salting those skewed keys, or you can leverage dynamic tools like AQE.
And speaking of AQE, or Adaptive Query Execution, it's an absolute game changer. By simply flipping spark.sql.adaptive.enabled to true, Spark dynamically changes join strategies at runtime and splits those skewed partitions on the fly. It's kind of like having an automated tuning engine working for you in the background while your query runs. Which brings us to pattern 4, memory and execution optimization. Let's look at how you're using resources under the hood. Let's clear something up about caching. It is not a magic make it go faster button.
You should really only use it when a data set is actively being reused or multiple actions depend on it. If you're out there caching one-time transformations, you're just wasting valuable executor memory and honestly slowing down your whole cluster.
There's another massive architectural distinction we need to uncover here. Calling the standard cache command locks you entirely into a memory-only storage level. But persist? That gives you options. It opens up memory plus disk configurations so you can safely overflow to disk if your data gets too big for your RAM.
So the main takeaway here, for developers and architects building serious, fault-tolerant production pipelines, persist is almost always the better choice. It just gives you the precise control you actually need over your cluster's resources.
Now, execution optimization is just as critical, and I've got 2 quick wins for you. First, get some free performance by swapping your data serializer to the highly efficient Cryo serializer. It's way faster than the default Java one. Second, and I can't stress this enough, avoid Python UDFs like the plague. They physically force data back and forth between different language environments, totally breaking Spark's native optimizations. Always prefer built-in Spark SQL functions instead.
All right, we've made it to Section 6, the Production Readiness Checklist. Let's verify before we deploy.
Before you hit merge on that pull request, or before you put down the marker in your interview, run through this exact list. Did you check your shuffle size? Is your join strategy actually correct? Is AQE enabled? Did you tune your partitions? Are you truly only caching reused data? Did you eradicate all those unnecessary Python UDFs? Systematically inspecting your physical plan against these exact points is how you guarantee your architecture is going to scale.
At the end of the day, mastering Spark optimization really boils down to this one simple equation. It's about logically locating the specific bottleneck and then applying the correct, matched pattern to fix it. Do that, and you can solve pretty much any performance issue thrown your way.
So, I'm going to leave you with this final provocative thought. Now that you know exactly which patterns and symptoms to look for, I want you to look closely at your own code bases. What hidden anti-patterns are secretly draining your production clusters right this very second? Thanks for hanging out with me on this explainer, and hey, happy optimizing!